Hello, dear students. Welcome back to our channel, Byte by Byte, where you'll be learning all the necessary and have the tools to be ready for advanced level computer science, ICT, and ordinary level computer science. Remember, if you are watching this video and you are not yet part of the team, do not forget to subscribe and join us in our WhatsApp channel and Telegram channel with the link in the description. Okay, in our last lesson, we introduced recursive functions. Today, we are going to see another way of executing or dry running recursive function and how to translate a recursive function to an iterative function very easily. We shall also see the different types of recursive function and we will conclude with the difference between an iterative function and a recursive function. Without wasting so much time, let us dive into the lesson. Dry running recursive algorithms using recursive tree. Yes, dear students, the alternative method of dry running recursive algorithm is by using a recursive tree. A recursive tree is a conceptual or visual representation of the recursive calls made by a recursive algorithm during execution. It illustrates how the problem is broken down into smaller subproblems, showing the hierarchy of function calls and their relationships. Each node in the tree represents a function call and the edges represent the recursive calls to subproblems. The leaves of the tree typically correspond to the base cases of the recursion. Now, dear students, why is a recursive tree an alternative method and why is it sometimes considered as the best method? Because we know that all recursive algorithm contains base case and recursive case, and for every recursive case, for majority of recursive function, there is a calculation that is done before the recursive part of the algorithm. And now a recursive tree is good because it helps us to visualize the hierarchy that we have for the different calls that are performed, and also it enables us to easily trace our result. Okay, let us take as example using the definition of the Fibonacci sequence given beside. Use a recursive tree to find the value of fib5. I'm sorry, it's supposed to be fib4. Okay, I earlier wanted to start with fib5, but due to the space, I decided to run by with fib4. Okay, if we are calculating the Fibonacci of 4, from the value of 4, we know that we are going with this case because 4 is above 1. So using a recursive tree, what do I have? Since the Fibonacci of 4 will be broken down into Fibonacci of 3, 4 minus 1, plus the Fibonacci of 2, which is 4 minus 2. I have my two leaves as you can see. So Fibonacci of 4 is given by Fibonacci of 3 plus Fibonacci of 2. And now I have to execute each of them. Fibonacci of 3, using the same definition, I am going to have Fibonacci of 2 plus Fibonacci of 1. And I apply the same concept here. I will have Fibonacci of 2 to be equal to Fibonacci of 1 plus Fibonacci of 0. And we are seeing that 0 and 1 are our base cases. So this is okay, as well as this one. When I break down this now, I have Fibonacci of 1 plus Fibonacci of 0. So from this tree, you can already visualize the hierarchy that we have, and you can already know the different calls that were done. 1, 2, 3, 4, 5, 6, 7, 8. So you see that for us to evaluate Fibonacci of 4, we are performing 8 recursive calls. And as said in the explanation, the leaves, as you can see, because a leaf is simply um, a node without a child. We shall understand best on this in our next chapter where we shall be treating data type and data structures. So as you can see, these are the leaves, and the leaves correspond to the base cases n equals 0 and n equals to 1. So now let us put their different values. Fibonacci of 1 is 1, Fibonacci of 0 is 0, as you can see. Each have their values. From there now, 1 plus 0 gives us 1, so Fibonacci of 2 is 1. 1 plus 1 gives us this 1 plus 0, 1. So Fibonacci of 2 is equals to 1, just like this one. Now, if I take this 1 plus this one, I'm going to get 2. That is why Fibonacci of 3 is 2. And once I take 2 plus 1, I get 3. That is why Fibonacci of 4 is equals to 3. So guys, this is an alternative way of executing recursive function by using a recursive tree. Very easy, as you can see. Now, let us look at another recursive function which is known as the tower of hanoi. The Tower of Hanoi is one of the main applications of recursion. It is a mathematical puzzle where we have three hots and n disk. We have three hots and we have n disk. Initially, all the disks are stacked. When we mean stacked, it means that the disk can be removed just from the top in decreasing value of diameter. That is, the smallest disk is placed on top and they are on hot A. The objective of the puzzle is to move the entire stack to another hot, obeying the following simple rules. So the Tower of Hanoi is simply a puzzle whereby we have three hots, A, B, and C, and we have n number of disks. And the objective is to be able to move all the hots from all the disk from hot A to hot C by using hot B as an intermediary. And now, while moving these different disks, there are some rules we have to follow. The first one is that only one disk can be moved at a time. The second one is that each move consists of taking the upper disk from one of the stack and placing it on top of another disk. That is, a disk can only be moved if it is the uppermost disk of the stack. Meaning that what? We cannot take the disk, we cannot take a disk that has another disk on top of it. So if I have disk X on disk Y, I cannot display disk Y if disk X is still on top. The next one is that no disk may be placed on top of a smaller disk. That is why it was said here. Initially, all the disks are stacked in decreasing value of diameter. That is, the smallest disk is placed on top. That's what we have. Okay. The algorithm: we move the top n minus 1 disk from the source to the auxiliary tower. So the source is A, the auxiliary is B, and the final is C. So the algorithm specifies that we move the top n minus 1 disk from the source to the auxiliary tower, then move the n disk from the source to the destination. As you can see, so our three hots here are the source, auxiliary, and destination. Then we have move the n minus 1 disk from auxiliary tower to the destination tower. And now we realize that from this algorithm that is given in step form, transferring the top n minus 1 disk from the source to the auxiliary tower can again be thought of, it can again be seen as a fresh problem and can be solved in the same manner. So as you are displaying n minus 1 disk from the source to the auxiliary, it is just as if I'm repeating the procedure again, but with this time around, my source remains the source and my auxiliary is like the destination, and the destination is like my auxiliary. So that is how it is. Viewing this problem, we see that it is a perfect application of recursion. And again until the disks are totally transferred from the source to the destination. Consider A, B, and C to be the source hot, auxiliary hot, and destination hot, respectively. The Tower of Hanoi can be recursively solved as: base case, if n is equals to 1, then we move the ring from A to C using B as spare. So if I have only one disk, I will just move that disk directly from A to C since it is alone. The recursive case, if I have more than one disk, what will I do? I move n minus 1 rings from A to B using C as spare. Then I move the one ring left from A to C using B as spare. And finally, I move n minus 1 rings from B to C using A as spare. So you see that here it just deals with the movement from one to the other using the other one as auxiliary. But it will be better for you to visualize how it is taking place. So the Tower of Hanoi, the case of one disk, as you can see, this is my source, this is my auxiliary, this is my destination. I need to move from A to C using this as auxiliary. So now, base case, I will just move A directly, I will just move the disk directly to C. This is what I'm going to have, and the problem is solved. For the case of two disks, this is what I have. So I need to move these two from A to C using B as intermediary. And the steps are that I can only move one at a time, and I cannot put a larger disk on a smaller disk. So the first step for this one will be for me, because we said that if n is above 1, the steps which further will move the n minus 1 disk to B, as you can see. So I first of all take this to B, and then I move the remaining one to C, and finally I move from B to C, as you can see, and the problem is solved. So this is how I have moved this two disks from the destination to the source using B as intermediary, as you can see. So that's how the tower of Hanoi is solved for two disks. For the case of three disks, is what we have. I want you students to put a pause on this video and try and figure it out by using the algorithm that was given to you and figure out how you will be able to solve the puzzle. So what do we have? We move the n minus 1 disk from A to B. So the first thing, as you can see, I take the smallest one and I put on C. Then I take this and I put on B. And I take this and I put back, as you can see. So this is what we have. It's not like I can move. So this is just a combination of two steps. That is taking this and putting on B, then taking this and putting on A. From there now, I will take this A and put on C. Sorry, this is even the same step. It's the same step. So this was supposed to be the step that shows how this one is coming on B. Okay, from here now, A will move on C, as you can see. Then this smaller one comes on A. Then B, this one comes on C. And finally, the one on A goes on C. And my problem has been solved. So this is how the tower of Hanoi is being solved for 1, 2, and 3 disks. Okay, let us look at the different types of recursion. Direct recursion. A function is said to be directly recursive if it explicitly calls itself. E.g., we have the factorial, the GCD, and the Fibonacci, because each of them call themselves. We saw it in their definitions. Indirect recursion. A function is said to be indirectly recursive if it contains a call to another function which ultimately calls it. E.g., function 1 containing a call to function 2 in its recursive case, and function 2 which has as recursive case a call to function 1. So that we call indirect recursion. That is, A in its recursive case calls B, and B in its recursive case call A. That's what we call indirect recursion. It is true we never had an example on it, but it is better, it will be good for you to understand. The last one is the tail recursion. A recursion function is said to be tail recursive if no operation are pending to be performed when the recursive function returns to its caller. When the call function returns, the return value is immediately returned from the calling function. Sorry, like the GCD. Realize that for the factorial, when I return, there is a multiplication that is performed. Same thing for Fibonacci, I am summing. But for GCD, there is no function which is returned, there is no value, sorry, which must be operated with the recursive case. No, it is only the parameters that are changing. So we can consider the GCD to be a tail recursion. Now we said when the call function returns, the return value is immediately returned from the calling function. Okay, converting recursive function to iterative function. To convert a recursive algorithm to an iterative algorithm, one eliminates the call stack overhead and often improves performance for large input. So when you are converting a recursive algorithm to an iterative one, you are eliminating the call stack overhead and will improve the performance for large input. The process generally involves replacing recursive calls with a loop and using a variable to track the state. The steps for the conversion are: 1. Understand the recursive algorithm. Identify the base cases and the recursive cases. Determine what state need to be tracked, the parameters or the intermediate result. Secondly, replace recursion with a loop. Use a loop, e.g. while or for, to mimic the recursive calls. Initialize variables to store the state that was passed between recursive calls, 0 for addition and 1 for multiplication. Remember when we were doing loop, we saw that such variables, how are they called? Accumulators. Perfect. We said that those variables which are changing inside a loop, those variables that are changing inside a loop must be initialized before entering to the loop. Either they should be initialized to specific values that are defined in the algorithm, that are defined in the problem, that are given in the problem description, or it should be initialized to 0 if it's supposed to change by 2 addition, and it should be initialized to 1 if it is to change by multiplication. The last step is to handle the base cases. We must ensure the loop terminates when the base case condition is met, returning the appropriate result. Okay, let us look at an example. So this is repetition algorithms part 2. The function factorial. I put this to be part 2 because from the translation you better understand how to write the iterative algorithm, because it is very easy to understand the recursive algorithm, and now if you can translate, then it will be easy for you to write the iterative version. The function factorial, as you can see, it takes one parameter n. Therefore, n equals 0 and 1, we should return 1. These are our base cases. Our base cases are for n equals 0 and 1. Else, we should return n times factorial of n minus 1. We are understanding here that we know the number of times iterate, first of all, for the factorial. We know the number of times we iterate, so it is a for loop you are going to use. The operation performed is multiplication. So the variable to store the state should be initialized to 1. Okay. So the first thing, I have function factorial n as integer. I have my variable count and result. We know that count it is because I'm going to use a for loop, and the result is what is going to track the values that were to be passed through the recursive calls. So first of all, I initialize result to 1, not only because of multiplication, but also because it is my value I will have if n is 0 or 1. And now we must first of all handle the base case. And yes, since I know the number of times I'm going to iterate, no need to handle the base case. The result is equal to 1. For count equals to 1, and what should we do? Result becomes result times count, because as you can see here, n times factor of n minus 1. So for each value of count, I will keep on multiplying the result and it will increase. So if count is 4, result will be what? 1 times 1, then it will be 1 times 2, then it will be 2 times 3, then it will be 6 times 4, then it will be 24 times 5, and that is how you are going to have it. And so we return our result, meaning that what? If count is 0, then result is 1. We are going to return it. If count is 1, this will execute only one time. 1 times 1, which is still 1. So the base cases are effectively handled. So this is the iterative version of the factorial function. The next one, the GCD, taking two parameters a and b. And our base case here is that what? A mod b should not be, a mod b should be equal to 0. Else, we must return GCD, where the changes we have are what? A becomes B, as you can see, and B becomes what? The remainder when A is divided by B. In this case, we don't know the number of times you have to repeat the loop. As you can see, we don't know the number of times to iterate. So a while loop. We loop till the base case, because that's what we say here. Ensure the loop terminates, and this condition goes only for the while loop, because the for loop, we know the number of times you are iterating. But if you are using a while loop, since you don't know the number of times you are iterating, we must ensure the loop terminates when the base case condition is met. And our base case here is that what? A mod b is 0. Now, there is no operation performed but change of variable. That is, a becomes b and b becomes the remainder when a is divided by b. So, I have my function GCD, my variable remainder, that is just like an intermediary, while a mod b is different from 0. My base case is that a mod b is equal to 0. So I must be looping till my base case is met. So my condition in the while loop should be the reverse of the base case. That's why I said a mod b different from 0. It means that when a mod b will be equal to 0, the loop will terminate. What should I do? Remember, that is, my intermediary takes a mod b, then a becomes b and b becomes that remainder, as you can see. And that is all. We return b at the end, because for the base case, what are we returning? B, and we end our function. So that is the iterative version of the GCD. I know that if I wrote the program normally, some will still understand, but I prefer to write the iterative version of the GCD here, so that from the recursive function you easily understand how we come about with the iterative version. That is the best way I saw for majority of students to understand how this algorithm will be written, especially the condition here and the different changes. And if you still find a problem, do not forget to leave me a message in the comment section. Okay, the next one, the Fibonacci. As you can see, our base case, n equals to 0 and n equals to 1, but I'm going to use the other form, where the base case is that we should return n if n is 0 or 1. So we know the number of times we iterate, so the for loop. We use a loop to generate Fibonacci numbers storing only the last two numbers, because remember, dear students, for the Fibonacci, we saw that as from the third term, each term is the sum of the previous two. That is why we use a loop to generate Fibonacci numbers, and we store only the last two numbers. I have my function Fibonacci n as integer, and I have my variable a, b, the temporal value, and count since I use a for loop. So if n is 0 or n is equals to 1, then I should return n simply, as you can see. Else, I first of all initialize the first two terms, because the sum of the previous term starts as from the third term. So for the first two terms, I know that a is 0 and b is 1. That's why I say for count equals to 2. And as I explained the other time, count equals to 2, that is where my third term starts, because for the Fibonacci, the first term is n equals 0, the second is n equals to 1, and the third term is n equals to 2. That's why count is starting from 2 right up to n. So what should happen? Temp takes what? A plus b. That is, this is now our third term. The sum of these two, this is now our third term. And now since we need to store, as you can see here, we need to store the last two numbers. We see that this is the first term, this is the second. In the for loop now, this is my third term. As you can see, the sum of the previous two. And after each iteration, I must have the last two terms. That is why a becomes b now. That is, this is now the first term, and b becomes, this is now the second term, and b becomes that third term. So at the end here, I will always have the last two terms, a and b. That's what we have, and we end for. And from there now, I return b, because at the end it is b that takes the last sum, and that is how I end with my function. So this is the iterative version of the Fibonacci sequence. I hope you greatly understood this. In case of any problem, you drop a message either in the comment section or in the Telegram channel. Okay, differences between recursion and iteration. Recursion terminates when a base case is reached, while iteration terminates when a condition is proven to be false. That's one difference. The next difference, each recursive calls requires extra space on the stack frame memory, because we saw that at every recursive call, there's a stack frame that is being created, while each iteration does not require extra space. If we get infinite recursion, the program may run out of memory and result in stack overflow, while an infinite loop from iteration could loop forever since there is no extra memory being created. Solutions to some problems are easier to formulate recursively, while iterative solutions to a problem may not always be as obvious as a recursive solution. Now, as you can see, those are the four differences we have between recursion and iteration, which is the same thing between a recursive algorithm and an iterative algorithm. And dear students, in another question, they will define you a particular function, like the factorial function, then they will define its definition in one manner, which will be recursive, and it will be, and they give this another definition in another manner, but for the same function a and b, then the how to differentiate between a and b, it is the same thing as differentiating between recursion and iteration. Let's remain concentrated. Iterative algorithms are generally more efficient in terms of memory and computational overhead, because they avoid the stack growth and function call cost associated with recursion. Also, iterative algorithms don't rely on optimization, providing predictable performance. So we are seeing that the overall iterative algorithms are more efficient than recursive algorithms, simply because they do not they avoid memory consumption and computational overhead. We are coming to the end of this wonderful lesson. See you in our next lesson, where we shall be introducing searching algorithms. Dear students, you are already coming to the end of the chapter, but do not worry. As soon as this chapter will be done, we are going to solve past questions, and you'll be directed to a link where you'll be able to answer MCQ on this chapter. And as many of you contributed in the WhatsApp channel, our next chapter after algorithms will be data type and data structures. Thank you for watching the video. Do not forget to like, to subscribe, and to share for our community to grow. Thank you very much.